Welcome back to the deep dive. Today, we are putting on our most technical hats. We're getting into an area where, really, chemical engineering collides with some incredibly demanding hydraulics.
We're talking about foam water sprinkler and spray systems.
Exactly. And we are diving deep into NFPA 16, specifically the 2019 edition.
And this is the standard that governs installations where, failure just isn't an option. Think about aircraft hangars, petrochemical facilities, large industrial process areas.
This is so far removed from your standard wet pipe plumbing job.
Oh, worlds apart. This is specialized chemistry that's being delivered by a very, very rigorously engineered piping system.
Absolutely. So our mission today is pretty clear. We want to provide a surgical, detail-oriented deep dive, and this is designed explicitly for you, the technical professional.
Right, the consulting engineer, the AHJ, the facility manager.
Anyone who needs to understand the non-negotiable requirements around these system types, the really stringent design criteria, and maybe most importantly, the complex mandatory acceptance testing procedures.
And it's probably good to set the boundaries right at the start. NFPA 16, it dictates the minimum requirements for design, installation, and maintenance, but, and this is a big but, it's limited exclusively to low-expansion foam systems.
That's a critical distinction. It really dictates the final application characteristic.
It does.
And those low-expansion systems, by their nature, they give you that essential dual capability.
Right, they're applicable to those combination hazards. So you have Class A fires, your, standard ordinary combustibles, and then the big one, Class B fires.
The flammable liquids that demand a very special extinguishing agent.
Exactly.
Yeah.
And before we really get into the technical minutiae, we should probably start where NFPA always starts, with the formal disclaimer. These standards are consensus documents. The NFPA is very explicit that they do not test, evaluate, or verify the accuracy of the information that's presented.
So if the document doesn't actually verify its own accuracy, what does that mean for the person, the engineer, who's relying on it to design, say, a $10 million fire suppression system?
It means the entire burden, liability, interpretation, professional judgment, it all rests squarely on the shoulders of the engineer.
So the standard is just a baseline.
It's the absolute minimum benchmark. But you, as the implementer, you have to exercise your own independent judgment. You have to confirm compatibility with the specific chemicals and site conditions, and then ultimately ensure compliance and suitability. This standard demands that level of due diligence.
Right, so with that crucial context set, let's start with the fundamental engineering goal. Why foam water? Why not just a massive amount of high-flow water?
Well, the rationale is pretty complex because it has to address different phases of a high-hazard incident. The primary goal, though, is crystal clear.
Extinguishment.
Extinguishment. The system has to provide foam solution discharge densities and water supplies that are sufficient to put the fire out entirely. We calculate the flow and the duration to achieve that specific goal.
But the design also has to consider scenarios beyond just putting the fire out immediately. What are those supplemental roles?
There are two major ones. First is prevention.
Prevention. How does a sprinkler system prevent a fire?
Well, in areas that are prone to spills, think of petrochemical loading docks or specialized manufacturing, the system can be manually operated to apply foam or water to hazardous material accumulations before an ignition source is even introduced.
Ah, I see. So it's a proactive measure against a really catastrophic scenario.
Precisely. And the second goal is what we call control and exposure protection.
Okay. And that's for when immediate extinguishment just isn't possible.
That's right. Control means you use the fixed discharge to allow for a controlled burn where, full extinguishment might take time, or maybe it isn't even the safest immediate strategy.
And exposure protection.
That uses the water spray component to reduce heat transfer to adjacent equipment or structures. It's all about buying critical time. And the effectiveness there is completely contingent upon the engineer correctly calculating and maintaining those necessary fixed discharge densities.
Now, let's get into the chemistry of the hazard itself. This feels like the fundamental constraint that changes the whole system design. We have to talk about the difference between hydrocarbon fires and polar solvent fires.
This is what the standard calls the critical chemical constraint, and it dictates everything about your concentrate selection. If you're dealing with ordinary hydrocarbons, gasoline, diesel, jet fuel, AFF, or aqueous film-forming foam is often very effective.
But if you are protecting an area that has water-soluble solvents and polar solvents, we're talking methanol, acetone, isopropyl alcohol.
You have a destructive problem, a huge one.
Because those polar solvents, they literally suck the water right out of a standard foam blanket, collapsing it almost instantly.
Precisely. They're miscible with water.
Yeah.
So the standard mandates that only alcohol-type foam, it's known as alcohol-resistant, or ARAFFF, shall be used.
And for you, the engineer, that immediately triggers a couple of complications.
2, right off the bat. First, you must consult the manufacturer for chemical applicability. And second, NFPA notes that the required application rates for these polar solvents may be significantly higher than the minimum design density required elsewhere in the standard.
So you're designing to the manufacturer's listed application rate, not just the base minimum in the standard.
Exactly. The chemistry completely overrides the baseline hydraulics.
It's fascinating. And for completeness, NFPA 16 is also very clear on where these systems are definitely ineffective.
Yeah, and this is important. They are completely inappropriate for liquefied or compressed gases, like propane or natural gas.
Water-reactive materials.
Like metallic sodium or potassium. Definitely not. And critically, electrical equipment, where the conductivity of the water component is just an obvious, massive safety hazard.
Right. It's a water-based solution. Non-conductivity is not an option.
Okay, so just like NFPA 13, NFPA 16 allows for these systems to be implemented as wet pipe, dry pipe, deluge, or pre-action systems. But that choice, it seems like it would drastically alter the maintenance and reliability profile. Oh, it does. Let's look at the extremes. Deluge systems are, in a way, the simplest mechanically.
Because they just use open discharge devices. All the sprinklers flow at once.
Right, but they're the most complex in terms of detection and water supply logistics. They rely completely on a separate, sensitive detection system, heat, smoke, optical for actuation.
Now, on the other end, you have the closed-head systems, and the most tempting one for speed has to be the wet pipe, or pre-primed, system. The lines are already full of foam solution, so the response time should be instantaneous.
The speed is the major benefit. I mean, it is the fastest, most reliable initiation you can get. But it introduces a massive headache for long-term reliability and maintenance. And as the engineer, you have to weigh that very carefully.
Because that foam solution is just sitting stagnant in steel piping for years.
For years.
Well,
And what does that stagnation do to the solution?
I can't imagine it's good.
It's not. NFPA is very direct about this. Foam solutions react with the steel pipe walls over time. This reaction causes sedimentation, corrosion, and crucially, oxidation.
And that oxidation chemically strips the foam concentrate of its essential firefighting property.
Exactly. It strips away its ability to form a stable blanket and film. So you could have a system that is hydraulically perfect.
But chemically inert. Useless.
Correct. So this deterioration means periodic draining, flushing, and repriming are absolutely necessary maintenance tasks. And then there's another critical design warning. Alcohol-type foams, the very ones required for polar solvents, are often not recommended for pre-priming because they degrade even faster.
So that forces a huge design trade-off, speed versus chemical reliability.
It does. For a high-stakes polar solvent hazard, you might have to sacrifice that pre-priming speed for long-term chemical integrity.
Which naturally leads us to the pre-action system, the classic compromise.
A pre-action system is designed to bypass that stagnation problem entirely. The piping is empty, or maybe it's supervised with low-pressure air. It uses a separate sensitive detection system to open the main deluge valve.
Which fills the piping with solution before the heat-sensitive sprinkler actually opens.
Right, so when the sprinkler finally activates, you get immediate foam discharge without having stored that degrading solution in the pipes for 5 years. It delivers the performance of a wet system while minimizing the corrosion and chemical breakdown.
You know, it's always instructive to see how these standards evolve. They're usually fixing real-world engineering failures or addressing new materials. What were the major shifts that led us to this 2019 edition?
Well, the 2011 edition was really foundational in recognizing the physics of modern foam agents. It explicitly introduced the clarification that alcohol-resistant foams behave as non-Newtonian fluids.
And that was a seismic shift.
It really was. Before that, an engineer might have just tried to apply the Hazen-Williams formula to the concentrate lines. The 2011 edition mandated consulting the manufacturer for friction loss, because these fluids, they just don't obey the simple viscosity rules of water.
So that really sets the stage for the complexity we see today. And the 2019 edition?
The 2019 edition focused heavily on structure and coordination. It was reorganized to align with NFPA 13, which creates a much more logical flow for planning, design, and installation. That's a huge help for any engineer familiar with the other standards.
And crucially,
it formalized the working drawing requirements, and it adopted the rigorous containment and drainage requirements directly from NFPA 30. And that really acknowledged that the system discharge isn't just water. It's a large-scale environmental and structural hazard that has to be managed.
Okay, let's move to the execution phase.
Mhm.
Before any trench is dug or any pipe is cut, the engineer has to produce the definitive blueprint, the working plans. And this documentation has to be exhaustive.
It truly must be. It has to be comprehensive and approved by the AHJ before any work begins. The standard spells out the mandatory detail, emphasizing that this is a fully documented, hydraulically based engineering effort. You need everything from structural details to the precise hydraulic path.
What are the key data points that would differentiate these plans from, say, a standard NFPA 13 submission?
The foam and hazard specifics are what's really critical. You have to provide, one, a hazard description, physical details, arrange it, and the specific identity of the hazardous material being protected, including all of its properties. Two, the foam specifics, the exact type and percentage of concentrate, say 3% FAR, the required application rate in GPM per square foot, and then the resulting calculation for the total amount of concentrate required.
And the piping specifics are more detailed, too.
Oh yeah. Beyond just nominal pipe size, the plans have to include cutting lengths or center-to-center dimensions.
Yep.
That's a level of detail necessary for specialty fabrication.
And there's a required visualization, a graph, that's a non-negotiable tool for verifying the supply.
That graph sheet is absolutely vital. It requires plotting 3 curves simultaneously, the available public water supply curve, the calculated foam system demand curve, and the required hose allowance.
And the intersection of the supply curve and the demand curve has to sit comfortably above the minimum required residual pressure.
Exactly. It provides graphical proof that you have the necessary hydraulic margin.
So let's focus on the lifeblood of the system, the water supply capacity. It has to be automatic and maintain the required rate for the full duration.
Right, and designing to the water supply often means dealing with a lot of external variables. If you're using a public water system, for instance, the engineer can't just rely on one static pressure reading.
No, that would be a mistake.
A huge mistake. The standard requires securing daily and seasonal flow and pressure fluctuation data from the water purveyor. The design must accommodate the lowest anticipated pressure condition, making sure the system functions reliably even during peak consumption times elsewhere in the utility district.
That's just good engineering practice, designing to the worst-case scenario. Now, how long does that supply need to last under full load?
The duration mandate is fixed, and it's substantial. The water supplies have to be designed to meet the calculated fixed fire protection demand, plus a mandatory 250 GPM for inside and outside hose streams.
And that total combined flow has to be maintained for
For at least 60 minutes.
60 minutes of continuous flow, plus a huge margin for manual firefighting. And that's regardless of how quickly the foam concentrate itself is depleted. That is a massive volume commitment.
It is. This is exactly why the coordination between the water utility and the fire system demand is so critical.
Yeah.
Any deficiency here just renders the entire system non-compliant from the start.
And the chemical component, the foam, introduces a serious regulatory hurdle with pollution and cross-connection.
Absolutely. Foam concentrate is a significant pollution hazard. The engineer has to ensure that any cross-connections are meticulously reviewed and approved by the public health agencies.
Right. And the annex stresses the need to determine if a listed backflow prevention assembly is required.
And that often necessitates highly reliable reduced pressure zone, or RPZ, backflow preventers to completely isolate the fire protection system from the potable supply.
Okay, let's look at the logistics of maintaining operational readiness. We can start with the mandated system discharge sequence.
The standard is very clear on this. Once the foam solution is depleted, the system shall continue to discharge plain water until it's manually shut off.
So it maintains the exposure, protection, and cooling phase. If the initial foam application doesn't completely extinguish the fire, the system doesn't just stop. It switches to a water spray cooling and control operation.
Precisely. And that continuity of supply is what makes the reserve supply mandate so crucial.
There has to be a reserve supply.
A readily available reserve supply of foam concentrate must be maintained, and its function is twofold. It has to meet the original design requirements and allow the system to be put back in service within 24 hours after an operation.
That 24-hour turnaround isn't about fighting the current fire, is it? It's more of a business continuity and risk mitigation requirement.
It's entirely logistical readiness. You have to ensure the hazard is protected again the very next day. The reserve has to be listed for use with the specific system components, and the AHJ has to sign off on how it's stored, whether that's dedicated separate tanks or just ensuring you have enough drums on site stored correctly to meet that full initial system charge.
Okay, let's dissect the components themselves, starting with the storage of the chemical agent. the foam concentrate.
Right. And foam concentrate is it's a temperamental chemical substance. It's very vulnerable to environmental changes.
And temperature is the primary culprit for deterioration.
It is. High temperatures accelerate the breakdown, and low temperatures increase viscosity, which makes proportioning difficult, if not impossible. The annex requires the storage temperature to be monitored and maintained strictly within the manufacturer's listed limits. Freezing is catastrophic.
And the rules against mixing different concentrates are absolute, which reflects how complex their chemical makeup is.
They have to be absolute. Different types and/or brands of concentrate shall not be mixed for storage unless you have documented proof of chemical compatibility and it's been accepted by the AHA.
What happens if you mix them?
You can get precipitation, a total loss of performance, or separation. It can literally turn the concentrate into sludge that just clogs up the proportioning equipment.
So even if they are both, say, 3% AFFF, if they're from different manufacturers, you have to verify compatibility.
You must verify it.
What about the physical requirements for the storage tanks themselves?
They need to be industrial-grade vessels, built for both pressure and chemistry. Atmospheric tanks need specific features: protected sight gauges, conservation-type vents to prevent foam evaporation, and dedicated space for thermal expansion of the liquid.
And if the tanks are pressurized?
Then they have to comply with the gold standard. The ASME Boiler and Pressure Vessel Code, Section 8, Division 1.
Okay, so the proportioning equipment is really the nerve center of this whole thing. It has to achieve a precise chemical mixture, say 3% concentrate, 97% water, no matter if the system is flowing at a trickle or at full blast.
The demand placed on this equipment is extreme, and the key design requirement forces the engineer to prove reliability across the system's entire operational envelope. The proportioning equipment has to meet the proper foam percentage for 3 very demanding conditions.
Okay, what are they?
1, the most hydraulically demanding condition, highest pressure loss furthest point. 2, the least hydraulically demanding condition, lowest pressure loss, closest point.
And the third one?
And this is the one people sometimes miss. Specifically, the flow of the most remote 4 sprinklers.
Let's linger on that for a second. The most remote 4. Why is that specific tiny flow rate so crucial for verifying a system that's designed to flow thousands of gallons a minute?
Because it represents the absolute minimum flow scenario required to initiate extinguishment in a closed-head system fire. This is the condition where proportioning equipment often struggles.
Why is that?
At very low flow rates, the hydraulic balance point is unstable. If the water flow is too low, the proportioner might fail to inject concentrate smoothly, or the pump might deliver an uneven flow. And that results in an initially weak, ineffective foam solution.
And you need that rich, correctly proportioned foam immediately.
Immediately. The system is designed to perform at its worst-case hydraulic conditions, and that means both minimum and maximum flow.
Okay, focusing on the foam concentrate pumps, they have to be absolutely reliable in these high-pressure environments.
Reliability starts with actuation. The pumps have to be automatic starting upon system actuation and fully listed for fire service under NFPA 20.
And to ensure injection into the pressurized water lines.
The pump's discharge pressure must, by mandate, exceed the maximum transient water pressure available at that injection point. An undersized pump simply means no foam injection.
But high-pressure injection always brings the risk of over-pressurizing the concentrate lines themselves.
Absolutely. So the standard requires a mitigation. If the pumps are capable of creating excessive pressure, a pressure relief mechanism must return flow back to the supply side.
And that's not just to prevent pipe failure, is it?
No, it also controls heat buildup in the pump itself, which can actually degrade the concentrate that's being cycled through it.
This is truly specialized piping. You can't just run standard steel pipe for pure concentrate. What are the materials constraints?
Compatibility is non-negotiable. The foam concentrate piping must be chemically compatible with the agent. The acceptable materials are all highly corrosion resistant: brass, bronze, and stainless steel, specifically 304 or 316.
What about carbon steel?
If carbon steel is used, it must be supported by the manufacturer's certification that the specific concentrate will not degrade it.
And then there's the warning that often surprises designers coming from standard systems, the galvanized pipe restriction.
Yes, the standard is crystal clear.
Right.
Pipe-carrying foam concentrate shall not be galvanized.
Why not?
The zinc coating on galvanized pipe reacts with foam concentrates. It leads to corrosion, and, more importantly, it forms soaps or sediments that can completely inhibit the foam's firefighting capability. This is a design mandate that you just cannot ignore.
Let's revisit the corrosion risk in the solution piping. We touched on this with pre-primed systems, but what's actually happening chemically inside that pipe over time?
So when foam solution sits in standard carbon steel pipe in a wet pipe system, the concentrate, which is often slightly basic or acidic, acts as a catalyst for corrosion and oxidation. Over extended periods, the chemical surfactants and the film-forming agents in the foam solution are literally consumed by the internal pipe scale and rust.
So if a fire occurs years later, the first slug of liquid that comes out is chemically weakened.
Or worse, non-functional. It takes time for fresh, effective concentrate to push all that stale solution out, and that risk heavily influences the choice toward deluge or pre-action for high-reliability systems.
Okay, we are now firmly in the engineering calculation domain. This is, without a doubt, the most complex section of NFPA 16. Let's start with the fixed minimum design parameters.
The baseline design density is 0.16 GPM per square foot, and the design area for closed systems, wet pipe, dry pipe, pre-action, is fixed at 5,000 square feet, unless a specific occupancy standard like NFPA 409 for aircraft hangars dictates a different area.
And this is where NFPA 16 really throws out some common NFPA 13 practices.
It does. The annex explicitly warns against applying the area modifiers from NFPA 13. You cannot increase the area for a dry pipe system, and you cannot reduce the area for quick response sprinklers.
Why is that?
The hazards covered by NFPA 16 are just so severe that the 5,000 square foot design area is the hard minimum required to contain and extinguish a Class B liquid fire.
And the duration of foam discharge is also fixed.
The minimum duration is 10 minutes of foam solution discharge over that design area, based on the 0.16 GPM per square foot rate.
But there's a small provision for adjustment.
Right. If the engineer opts for a higher application density, say 0.20 GPM per square foot, the duration can be reduced proportionally to save on concentrate cost. But, and this is key, under no circumstances shall the discharge duration be less than 7 minutes.
The 7-minute threshold is the non-negotiable floor for effective Class B extinguishment.
It is.
Now, engineers typically run one worst-case calculation, but NFPA 16 demands two for closed systems. You need the most demanding and the least demanding conditions.
This dual calculation mandate is the standard's way of ensuring the system works correctly across its entire operating pressure range. You have to calculate flow and pressure for, one, the most hydraulically demanding condition.
Right, that confirms the system can overcome friction loss and deliver the minimum required density at its weakest point.
And two, the least hydraulically demanding design area. This is often the closest set of sprinklers to the riser or pump.
Why obsess over the least demanding area? That's where you have the highest available pressure. Shouldn't that be the easy part?
It's counterintuitive, but it is crucial for proportioning stability. The annex explains that if the pressure is too high, the resulting flow rate can actually overwhelm the capacity of the proportioning device.
So if the proportioner is rated for, say, 1,000 GPM maximum, and the least demanding area forces 1,200 GPM through the line,
then the proportioner cannot inject the necessary volume of concentrate, and your solution concentration drops drastically, potentially below the mandatory minimum.
so the system could actually fail by being too efficient at flowing water.
Exactly. And that leads us directly to the verification check.
What's that?
The verification check is the proof of concept for the foam supply. The hydraulic balance must demonstrate that the actual system discharge, calculated at the most demanding condition, will not exceed the capacity of the foam concentrate supply to maintain that minimum 7-minute runtime.
So if your system flows too hard and depletes the 10-minute supply in 6 minutes, the design fails.
The design fails.
Mm-hmm.
You have to prove the math holds for the duration requirement under the maximum flow conditions.
Okay, this next part is the section that I think really elevates foam engineering above standard hydraulic engineering. For the water and foam solution lines, we stick with the standard Hazen-Williams formula.
Right, using NFPA 13, C values 120 for new steel, 100 for dry pipe, and so on. But when you're calculating friction loss in the pure foam concentrate lines, we abandon Hazen-Williams entirely.
Completely.
That's right. Friction loss in lines carrying pure foam concentrate shall be calculated using the Darcy-Weisbach formula. Hazen-Williams assumes a constant C value because water's viscosity is largely predictable. Foam concentrate, particularly ARAFFF, does not behave like water.
So why is Darcy-Weisbach mandatory here? What is it accounting for that Hazen-Williams just misses?
It accounts for the actual slow characteristics of the fluid, specifically the Reynolds number. Foam concentrates are often non-Newtonian fluids.
Which means their viscosity isn't constant. It changes based on the shear rate or how fast the fluid is flowing through the pipe.
Precisely. Some AR foams are shear thinning, meaning their viscosity decreases as flow increases, while others might exhibit really complex, nonlinear behavior.
So you can't use a fixed C value because the smoothness of the flow, its friction factor, is constantly changing based on velocity and temperature.
Exactly. The Darcy-Weisbach formula requires the engineer to calculate the Reynolds number, or R. To do this, you need two critical pieces of proprietary data from the foam manufacturer: the actual density, or specific gravity, and the actual viscosity of the concentrate.
And the viscosity measurement is crucial because of its temperature dependency.
It must be measured at the lowest anticipated storage temperature. Viscosity typically skyrockets when the temperature drops, leading to massive increases in friction loss. It can sometimes render the concentrate pump ineffective if it's not accounted for.
So you get the Reynolds number, and then what?
Then the calculation allows you, the engineer, to consult the Moody diagrams, which are in the standard, to derive the friction factor, F, which is then applied in the Darcy-Weisbach equation to get the accurate pressure drop.
This forces the engineer to function as both a chemical engineer and a hydraulic engineer simultaneously, and to rely on proprietary data that standard practice just doesn't require.
And if you're dealing with one of these non-Newtonian AR foams, the standard requires an extra step.
Which is?
It reiterates the mandate from 2011. You must consult the manufacturer for the friction characteristics. This acknowledges that the standard Moody diagrams may not perfectly represent the highly specialized rheology of modern AR foams, and you might need proprietary correction factors.
You have to prove the pressure loss calculation based on verifiable manufacturer-supplied data. No guessing.
No guessing.
Okay, we've saved perhaps the most logistically challenging design requirement for last in this section: managing the vast volume of liquid that results from a 60-minute firefight.
This is where the structural and civil engineering teams get involved, coordinated through the standard and NFPA 30. The design must provide means for the safe removal or containment of the largest anticipated flammable liquid spill, PLUS, the total volume of free water reaching the floor from the fixed fire protection system, including hose streams.
This isn't just a fire protection problem, this is a flood control problem.
It is. I mean, we are talking about containing potentially flammable, toxic, and environmentally hazardous runoff. Let's just run the illustration that's provided in the standards annex.
Okay.
A 5,000 square foot area, minimum design density of 0.16 GPM per square foot, plus the 250 GPM hose allowance running for the mandatory 60 minutes.
So the total flow is what, 1,050 gallons per minute?
Over 60 minutes, that results in a minimum containment volume of 63,000 gallons.
63,000 gallons.
And that's before you add the volume of the original spilled liquid and any water that's used manually.
That is the size of a small municipal water tower contained within the facility's footprint. The engineering implications of that volume are just staggering.
They are massive. You need serious civil engineering. Drains have to be sized to handle 1,050 GPM continuously, which often requires trench drains or containment dikes. The structure itself, the floor slab, the foundation, the retaining walls, it all has to be designed to withstand the hydrostatic pressure of tens of thousands of gallons of liquid.
And the containment area is limited.
It has to be limited to the system design area, which forces localization of the spill management efforts. This one regulation fundamentally shifts the cost and complexity of the entire project.
Okay, all the calculations, all the proprietary data, all the specialized piping, it all comes down to the acceptance testing phase. Chapter 8. This is the field verification that everything performs as it was modeled.
This is where the paper meets the pipe. Acceptance tests have to ensure the hazard is fully protected, verifying flow pressures, actual discharge capacity, and, critically, the foam consumption rate.
And if multiple systems might operate at the same time on a large hazard, they have to be tested at the same time.
That's right. The standard mandates simultaneous foam discharge of the maximum number of systems expected to operate on a single hazard. This tests the adequacy of the water and concentrate delivery system under its absolute peak load. If the pressure drops too much across two simultaneous flows, the design fails.
Let's focus on the absolute core of foam reliability: the proportioning system testing. You need proof that the chemical mixture is right.
For closed systems, the flow test must verify the concentration at two specific points, which mirrors our dual calculation mandate.
So you're testing at the least hydraulically demanding condition.
And the flow of the most remote four sprinklers.
Right. We've established why the most remote flow is so crucial. It's that minimal flow where instability is most likely. What is the allowable tolerance for error in the concentration measurement?
This is perhaps the most demanding mandate in the entire standard. The concentration rate must fall within -0% to +30% of the manufacturer's listed concentration,
Or,
or plus 1 percentage point, whichever provides the lower allowable upper limit.
so if the listed concentration is 3%, you absolutely cannot drop below 3.0%. And your upper limit is either 4.0%, that's 3% plus 1 percentage point, or 3.9%, which is 3% plus 30%. So you have to use 3.9% as your upper limit. Why the strict -0% requirement?
Because anything less than the listed concentration means the foam blanket will likely be too weak to withstand the heat and the surface tension demands of a Class B liquefier. It just won't work.
And the plus 30% allowance.
That gives the engineer a slight margin for field conditions and component variations, recognizing that a slightly richer solution is generally acceptable, but undersizing is an immediate failure.
In the field, how difficult is it practically to hit that tolerance, especially at that low flow condition of the 4 remote sprinklers?
It is extremely difficult. Proportioners often rely on differential pressure or mechanical linkages. At minimal flow, water turbulence, vibration from the proportioning pump, minor temperature fluctuations that impact concentrate viscosity. All of these things can cause momentary fluctuations outside that narrow band.
So technicians spend a lot of time tuning these systems.
A significant amount of time, yes. Often making adjustments at the low flow rate to ensure they never dip below that 0% mark while still maintaining efficiency at a high flow.
So once we flow the system, how do we prove the mixture is correct?
The verification is done using precise laboratory-grade methods, either refractometric means or the conductivity method.
And there's a crucial note in the annex about that.
There is. Refractometry, while simple, is often not accurate for AFFF and ARAFFF foams, especially when they're mixed with non-potable or brackish water.
Because of their low refractive indices.
Exactly. The conductivity method is generally preferred, provided you have a good baseline conductivity reading of the plain water supply.
And the cleanup after the test. The mandatory flushing protocol.
Deluge and spray systems must be flushed with clean water immediately after foam operation. You cannot leave that residue in the lines because the foam will degrade and corrode the components, especially the strainers and nozzles.
And finally, the foundational pressure check. The hydrostatic testing.
All system piping, including the foam concentrate lines, must be tested at 200 psi or 50 psi above maximum static pressure if that pressure is over 150 psi.
And that pressure must be held without loss for a rigorous 2 hours.
2 hours. It's the non-negotiable structural integrity check.
This last chapter reinforces that the engineer's job doesn't end when the flow test is complete. It really ends when the system is fully documented for the next 40 years of service. And that starts with mandatory signage.
Yes, the standard demands 2 permanently marked, weatherproof signs secured with corrosion-resistant fasteners. And these signs are life-critical for future maintenance personnel who might not have access to the original plans.
The first one is the hydraulic design information sign placed at the main system valve. What critical data from the hydraulic calcs must be posted right there?
This sign is basically the summary of the design performance, and it enables maintenance crews to conduct future performance tests. It needs the location of the design areas, the required discharge density, the required flow and residual pressure for both the most and least hydraulically demanding calculations. That is crucial for verifying proportioning balance later on.
Yes.
The foam solution discharge duration, so 7 or 10 minutes, and the hose stream allowance that was included in the calculation.
This sign really transforms the system from a black box into a testable, traceable component. And the second sign, the general information sign, provides the chemical and occupancy context.
This one is placed at each system control riser, and it addresses the specific hazard the system was designed to protect. So you'll have the occupancy and commodity classification.
High-piled storage, max storage height, things like that.
Right. The presence of specific hazardous materials or flammable liquids, the specific foam concentrate type and percentage, and critically, if any corrosion inhibitors are used, the chemical type, concentration, and proper disposal information. That's vital for safety when maintenance personnel are flushing the system.
Okay, moving to the long-term operational mandates. The standard emphasizes allowing testing and inspection without actually discharging foam solution.
This is a huge economic and environmental imperative. Foam concentrates are extremely expensive and require special disposal after use. So the system has to be arranged with specific test connections or bypass valves to allow the mechanical and electrical components, pumps, proportioners, valves, to be tested functionally without wasting thousands of gallons of concentrate.
And beyond just adhering to the testing frequencies in NFPA 25, what other essential logistics need to be maintained?
The requirement for spare sprinklers is carried over from NFPA 13, but its importance is still there. You have to maintain a fully stocked spare sprinkler cabinet for all types and ratings present, clearly listing the specifications: SIN, K-factor, temperature rating.
And the final mandate for the contractor is providing the owner with the full package of documents.
Yes. The contractor must provide the owner with all the literature, the full set of working plans, the final hydraulic calculations, and a copy of NFPA 25. This ensures that facility maintenance personnel, long after the installation team has left, have the necessary technical foundation to maintain compliance and operational integrity.
We have navigated the incredibly dense regulatory environment of NFPA 16. For the engineers listening, let's try to synthesize the three most rigorous, high-impact technical requirements that really separate this discipline from standard water-based fire protection design.
Okay. First, I'd say it's the recognition of non-Newtonian fluid mechanics. The chemical nature of the concentrate forces you away from Hayes and Williams.
Yeah, you have to move to Darcy-Weisbach.
You have to.
Yeah.
And that requires proprietary data on viscosity at the lowest temperature, calculating the Reynolds number and referencing UDI diagrams.
Yeah.
It just demands a much higher level of chemical and flow modeling sophistication.
Okay, number two.
The monumental logistics of containment and drainage. That non-negotiable 63,000-gallon minimum containment volume for a standard 5,000 square foot area, it forces a collaboration with civil and structural teams under NFPA 30. The design shifts from simple piping layout to large-scale infrastructure planning to manage a potential flood of hazardous runoff.
And third.
The extreme precision required in proportioning tolerance, meeting that -0% to +30% tolerance across the entire flow envelope, especially at that critically unstable low-flow condition of the most remote force sprinklers. It demands highly specialized, precisely calibrated, and actively managed proportioning equipment to guarantee chemical effectiveness right at the moment of fire initiation.
It's clear NFPA 16 is a masterclass in interdisciplinary engineering. It requires expertise in chemistry, fluid dynamics, environmental regulation, structural integrity. It's a truly engineered solution for the highest risk scenarios.
Absolutely.
Yeah.
And that, I think, leads to our final provocative thought for you to consider. Given how much is invested in calculating complex flow paths and sizing pumps, and recognizing that concentrate properties fundamentally change based on temperature and age, which impacts your Darcy-Weisbach friction factor calculation, is the annual sampling and factory testing of the foam concentrate itself, as recommended in the annex, the single most overlooked and underappreciated factor in ensuring the operational integrity of these highly complex, life-critical systems.
Something to mull over as you review your next set of foam water plans. Thanks for joining us for this deep dive.
Until next time.